Hello, welcome in video 24 in the lecture Advanced Mathematic Modeling. So in the last video I introduced you to the random walk, which is given a stochastic process of the increments EI, which just by summing up we can calculate a new random process of the state xi, or the position of a walker. And now we want to calculate some properties of the random walk. So the first is that you see, of course, that you can sum these equations up. So, I mean, this definition is written as an increment in time. So how does the state change from one time step to the next? And you, by iteration, you can directly see that we can also write down, do it like this, so you have more space to see. So we can write down the position at a certain time point n directly as the sum of all the increments from I equal 1 until n. Yeah. So some people directly use this here to describe the random number. You could also, if we are correct, we also should maybe write here, maybe I should write it in a smaller, we should maybe add here the position at time 0. Yeah, but I do it only here in a small font because we then say we start at 0 because that's just a shift of the whole thing, and then typically we say just the initial value is 0, and we're just interested in the sum of random numbers. So random walk is just a sum over n random numbers. Maybe if you look carefully, you see that's maybe I made here maybe a mistake. You could have said I should sum here from I equal 0 to n minus 1 to be concise with this here. Yeah, maybe I should have done this, or here I could have written you sum xi plus the increment from I minus 1. Yeah, so yeah, and then sometimes I start always from the first times at 1, and sometimes I start at 0. So because people use, different authors use this a bit different, but you will always know from the context. So maybe if I take this equation here more correct, I would have said we sum from I equals 0 to n minus 1. But basically what we mean when we, but that's just a shift in the increments. It remains that the nth value of the random walk is the sum over n random numbers, and here maybe expressed like this, it's a bit more simple to see it. So okay, now we have this definition here, and now we want to see, can we calculate now properties of the random walk? And maybe the first we could be interested would be the mean value. So what is the mean value? Mean value of our walker. So we want to calculate here the expectation value, which is a function of time. And now there's different ways we can write this down. So we could either put this n here as an index, and sometimes I use a different notation. I write here x, and then write this is a function of time. So I use this notation to see really it's the whole thing is a function of time. Yeah. So, and again, different authors use the notation a bit different, and I cannot ensure that I will always be consistent. Yeah? Okay, now we want to calculate this. So we can now, and the fundamental question, of course, was how can we calculate these from the properties of the increment that I showed you in the last video? That's the question. So let's plug in here this formula. So we have to calculate the expectation value of a sum of n random numbers from I equals 1 to n. And so this x0 we just set to 0. Okay, now the expectation value is a linear function, so we can write down the sum of expectation values of our EI. I equals 1 to n. So now how do we proceed? And now we need to, in order to simplify this further, we have to assume that we have a stationary process. And so in a stationary process, I showed you that the expectation value is a constant, so it's independent of time. And then this expectation is always the same. And then we can just write down this is n times the expectation value of our random process. And this we can do if we have a stationary process. And so that will be our assumption, typically, that the increments are stationary. Remember this, they can still have a memory in time, they still can have autocovariance function, which is non-trivial, but they should be stationary. So this means and the moments like correlation functions should not depend on absolute time. And then in particular, the mean value of the increments should not depend on time, and then we can write it like this. So that's the first property that we have. The expectation of our random walk in time equals just n times the expectation of the increments. And now, in particular, if we have a random walk which has no bias, and no bias actually just means that the expectation of the increments is 0, and this was just the examples I showed you before. So when the distribution of the increments has mean value 0, so that we have the same chance to go up and down. Yeah. So it's kind of there is no bias to one positive or negative direction in the system. Yeah. And then from this formula we see that then also the expectation for the mean position of our walker will be 0. And then we see, okay, in this case the expectation value of our walker will be always 0. So that's the most fundamental. So if we have a symmetric random walk, the mean value of the walker is 0, even though we will see that's the most unlikely place the walker will be. So random walk theory, even though everything looks simple, when you dig in a little bit deeper, suddenly there is a lot of bizarre results. And this is one of the bizarre things, that when you look what's the chance that the random walker actually will be 0, it's very small. It will be either positive or negative, which we'll see later. But the expectation value will be 0, which is clear by symmetry. I mean, if the increments are symmetrically plus and minus, then in one realization you might be more on the upside, in another realization you might be more on the lower side, but on average, by symmetry, the mean value of the walker also has to stay 0. And then if you have now a small bias and you have the increments have a certain bias to be positive or negative. So it's good, for example, you have your Bernoulli trial with a coin which is not fair, then the sum you earn by throwing this coin a lot of time, so the mean walker has a position which might increase in time. So that's the mean value of a walker. So that was quite simple. Now let's see, can we calculate the standard deviation? Yeah, so for this we need to calculate the second moment. So let's calculate the second moment x squared as a function of n. So what we need the expectation of our sum of n random numbers, I equals 1 to n, and this sum has to be squared. So now, in order to see what this means, it helps to write this down in a simple way. So the sum here means we have the first increment plus the second plus the third and so on. And then we have to multiply this again. First increment plus the second increment plus the third increment and so on. And from all this we take the expectation value. Now we can multiply this out so that we remove the parentheses. And so what do we get? So we get an expectation of a lot of sums. And let's order this directly. So we have first here E1 times E1. So we have here E1 squared. Then we also will get a term E2 squared. We get a term E3 squared. And so until plus En squared. And then we get all the mixed terms plus. So maybe right down here we have n such terms. And then we get the mixed terms, so we have E1 times E2. Then we have plus E1 times E3 and so on and so forth. Then we have E2 times E1. Then we have E2 times E3. E2 squared is already gone here, plus, and so on and so forth. And from all this we take the expectation value. Now the expectation value is again linear, so now we have a lot of sums, so we can take the expectation value of every sum. And now we assume again we have a stationary process, so we can write down the first terms here. So we have n times the expectation value of the EI squared, because each of this has the same expectation value. So we have n times this. And then we have here the expectation value, the sum of expectation values, plus a sum of all these expectation values EI times EJ, yeah, where we assume that I is not equal J. That's the famous correlation sum. And this gives us the second moment expectation as a function of time. Yeah, so it's kind of straightforward to calculate, and if we compare it to the mean value, so here we have two components. If you take the second moment, we have something which looks like here for the mean value, but then we get also the sum of all these covariance functions. And now what's happening if we have no memory in the system? If we have no memory, and we assume that all these moments are this let's see how would we say it. Yeah, basically if the increments are independent. So let's assume we have an identical independently distributed random numbers, an IID process. So, and then we know that the increments will just this autocovariance function of the increments is just in the form of a Kronecker delta. If I equals j, then we have here the variance, because then we just have I squared. And if I and j are different time points, then the covariance is 0, because we have no memory in the IID process. So we have here the Kronecker delta. Yeah. But in this sum here, we sum only over these values where I is not equal j. And that was the whole point, to separate in this sum here all these values where we have the same time point, where we can write down the square, and these points where we have increments at different time points. But for an IID process, all of these vanish. And then we see for an IID process, then we see that the second moment as a function of n equals n times, and this here is again the variance sigma squared. We call this the variance as we had before, and then we find this fundamental property for an IID process. We call this quantity here, in random walk theory, this is often called the mean squared displacement. So this here is a function of n. It's the mean squared displacement. And so we see for an IID process, the mean squared displacement goes proportional to time. And so we see now, so here the mean position of the walker goes linear in time. And for an IID process, the mean squared displacement also goes proportional to time. Whereas in a general process, the mean squared displacement goes proportional to time plus the sum over these memory functions. Now let's see what this means for the random walk. Let's first how a random walk looks when it has bias or no bias. So let's have a random walk with bias. So this means the expectation value of the increments is, for example, larger than 0. So what does it mean? So if we take the position of the walker as a function of time, x, maybe here we always use the symbol n, and now, so we know from our theory so that the mean value should go proportional with time. So we know that the mean value of the walker should be a linear function of time, because so we know that the expectation value of x should be proportional n. But now if we take a realization, the realization might still look like something like this. Another realization might be like this. Another realization might be like this. So we have again different realization, give random profiles which scatter up and down. But if the increments have a mean value which is not zero, which is biased, so if we have a bias here and the bias is positive, we have a higher chance that the increment is positive, and then it's clear that the mean value, the mean position of the walker on average will increase proportionally to time. So this result that we found here is following directly the intuition. And now maybe take a random walk without bias. So we have that the expectation values of the increments is 0. So we take the random walk. We have here time. We work the x. And now we can have again our realizations. And in this case, now the realizations are in such a way, they're still scattered around, but now the expectation will stay 0. And now the question then one could ask, okay, so I know on average that the walker has position 0, but I still would be interested to know what's the likelihood to find it somewhere. How far should it be? Should the walker be away from 0? So I would like to know what's the typical displacement that the walker has at a certain time point. So if I take this time point here, I would like to know, so what's the typical range that I think the walker should be. So what's this range? And you see this range is increasing because here it started with 0, the range was very small and then was increasing. And now how can we calculate this range? So that's the range that would be the standard deviation of the walker. So here we calculated the second moment. So basically it's the variance, because like the mean value is 0. So first let's write it down. We let me see, should I write it here or there? Let's write it up here. So we know that so let's assume now we have an IID process. Keep it simple. Assume we have an IID process. So, and then we have seen that the second moment as a function of time goes with the variance times time. And now, okay, so like, and since the mean value of the walker, so in this case here, of course the mean value equals 0. Since the mean value equals 0, so this is automatically also the standard deviation. So x squared minus the mean value squared, in this case, is the same as as x squared. Maybe I write it again so that, because the mean is 0. So actually this here, this mean squared deviation, is equals the variance of the walker. But we are interested in the standard deviation. So the standard deviation. So what is this? That's the square root of this. So we need the square root of the second moment as a function of n. And that's the typical deviation that the walker, the typical deviation from zero that the walker will have. And so when we calculate this, we see this goes as the standard deviation of the increments times the square root of n. So the typical deviation of the walker from zero and in random walk theory we call this the typical displacement. And so we see the typical displacement goes with the square root of n. The square root is this function here. Yeah, so it's increasing with the square root. And so we know that the typical displacement of the walker goes with the square root of time. So if we have the drunken man which goes up and down randomly, and if you know how long does he need to take her to manage to travel a certain distance from his starting point, so the distance he on average travels goes with the square root of time. And so why we need to go by this? Because like the displacement can be either up and down here, which averages away. So we first have to calculate the squared displacement, so that we really get the absolute distance, and then we take the square root again to get the typical displacement of a walker. Yeah? And this goes only for an IID process. If we have a process with some memory, yeah, it's not clear if this holds. Yeah? But for an IID process, if we have independent random numbers, the displacement goes with the square root of time. So maybe let's write this also down. So the typical displacement, if we have an IID process, then we have the mean squared deviation grows with square root of time. So to summarize, in this video I showed you I made this very slowly because these are important for later things we do with random walk, so I wanted to make sure that you really follow me here. So we calculated the expectation value of a random walker, we calculated the second moment as a function of time, and we looked how this simplifies in an IID process. And so we have seen now the typical properties of a walk. A walk can be either biased, so the mean value is increasing linear in time, or the walk can be non-biased. And biased walks basically you can always avoid, because we always can then go to a slowly moving coordinate system. So typically we can drop out the bias. If we know there's a bias, we go to a different coordinate system and just remove the bias. So yeah, the interesting properties are not hidden in the bias here. So very often we assume we have here symmetry. And then we saw that now with a symmetric random walk, then we see that the standard deviation, that's what the typical displacement a walker can have, goes with the square root of time. If we don't remove the bias, then of course you see the square root also. So basically here we could also draw in here the square root of time, so it would be square root of function which additionally grows linearly. So we have also this envelope basically of all the trajectories, or not the envelope, the typical width of this cloud points of all trajectories, which grows as a square root but centered around this mean value, which increases in time. So I stop here, and in the next video we will discuss this a little bit further. Okay, thank you.